Hello, my name is Hokun from Seoul St. Mary Hospital. The title of our study is Conversion of Mixed Language Pretext Sheet Reports of Pancreatic Cancer to National Comprehensive Cancer Network Structural Reporting Template by using GPT-4. Imaging plays a critical role in determining the resectability of PDAC following NCCN guidelines. However, inconsistent reporting due to individual preference and workload remains a challenge. Structured reports help improve clarity, accuracy, and consistency in radiology, while also enabling easier data extraction for research. Manual conversion from pretext to structured reports is both labor-intensive and prone to errors, but recent advancement in LLMs offer promising solutions. LLMs are flexible in processing text across different languages and have the potential to generate structured reports without domain-specific training. Our study aims to evaluate the feasibility of GPT-4 in generating structured reports from mixed language, especially English and Korean, narrative style CT reports for PDAC, and to assess its accuracy in categorizing PDAC resectability. This figure shows the overall study flowchart. The study is divided into two parts, each conducted on independent datasets. Prompt engineering step focused on prompt optimization, while model testing step involved structured report conversion and performance evaluation. We developed a customized structured report template and resectability criteria based on the NCCN guidelines with modifications to elements that typically require multidisciplinary consensus. The final template consists of 16 key evaluation items, including resectability assessment. This table shows the customized structured report template used in the study. And this table shows modified resectability criteria. We collected free text report from consecutive patients referred to institution A over 3 years. Exclusion criteria were absence of pre-treatment staging CT, not conforming to the pancreatic protocol CT, and cases without radiology report provided by attending radiologist. In this slide, I show two representative examples of free text reports. One example is written using a combination of Korean and English letters, and the other is written exclusively in English letters. One experienced abdominal radiologist manually converted the free text reports into reference standard structured report dataset using in-house software, relying solely on the original narrative report without referring to images or medical records. The prompt engineering process developed optimized English-only prompt using the GPT-4 turbo model. Iterative optimization was conducted with a mixed language report from institution B to enhance accuracy and decision rational clarity. Explicit instructions for vascular involvement and liver region interpretation were incorporated through feedback loops, and free-shot prompting was implemented using structured example output. Each report was converted 3 times due to the inherent stochastic nature of LLMs. The most frequent response was selected as the final output, and if all 3 responses were different, the first session's response was used as the final output. Outputs were considered correctly only if they exactly matched the reference standard. Any outputs that included items not in the template, were in incorrect formats, or deviated from the prompt instructions, were classified as incorrect. GPT-4 Turbo and GPT-4o models were used for structured report generation, with the model temperature and frequency penalty set to 0. All input and outputs were automatically transmitted and stored using a Python script with the OpenAI API without pre-processing. Conversion errors were classified into 4 main types. 1. Data ambiguity. 2. Fictitious data creation. 3. Incorrect reporting. 4. Data omission. For reflectability assessment errors, 3 categories were used. First, incorrect judgment of vascular involvement metastasis but correct application of resectability criteria. Next, correct judgment of vascular involvement metastasis but incorrect application of resectability criteria. Finally, incorrect judgment in both vascular involvement metastasis and application of resectability criteria. Statistical analysis was conducted using the Python statistical libraries. Performance was measured by accuracy, and free marginal kappa and percent agreement were used for repeatability evaluation. The McNamara test was used to compare GPT-4 Turbo and GPT-4. Finally included reports consist of 115 from institution A and 50 from institution B. The reports were written by 11 attending radiologists, with 140 reports written using a combination of Korean and English letters, and 25 reports written exclusively in English letters. This slide shows an example of the automated LLM model output implemented using OpenAI API and Streamlit library. The input free text report is automatically delivered via an Excel file, and the output contains a CSV format output with detailed rationale for the evaluation of all items, including resectability. In 3 repeated experiments, both models demonstrated high repeatability across all items. The lowest kappa and percent agreement were observed for resectability in both models. Of 1,725 reference standard items, GPT-4 Turbo correctly reported 1,592, which was slightly higher than that of GPT-4O, although this difference was not statistically significant. For resectability, GPT-4 Turbo achieved 81.7% accuracy, which was higher than that of GPT-4O, 67.0%. For both models, no significant differences were found in the extraction of key items from reports written in English only or in a mixture of English and Korean. For resectability assessment, GPT-4O showed a significantly higher accuracy when using mixed language report. In the test set using GPT-4 Turbo, 133 errors were identified, representing a 7.7% error rate. The errors were mainly due to data ambiguity and incorrect reporting. For resectability, 21 errors were identified, yielding on 18.3% error rate, mainly due to correct vascular involvement metastasis judgment, but violation of resectability criteria. In comparison, GPT-4O showed 173 errors, equating to 10% error rate. GPT-4O further produced 38 errors in 115 assessment of resectability, corresponding to an error rate of 33%, mainly due to incorrect vascular involvement metastasis judgment, but correct application of resectability criteria. This study identified 2 key findings. First, both GPT-4 Turbo and GPT-4O successfully generated structural report from mixed language data with comparable overall accuracy. Second, GPT-4 Turbo demonstrated superior resectability accuracy. Performance influenced by ambiguity and inconsistencies in original narrative reports. Clearly defined items such as size, location had high accuracy, but ambiguous items such as liver regions, suspicious lymph nodes reduced accuracy. Standardized terminology and clear definitions suggested to improve future LLM performance. Models effectively handled mixed language input without significant accuracy loss. Similar performance observed in studies with Italian, Portuguese, Japanese, German, and Chinese report. Findings support multilingual adaptability of LLMs in clinical applications. GPT-4 Turbo outperformed GPT-4o due to the tailored prompt optimization. GPT-4o, despite the recent advances, shows lower accuracy due to absence of specific prompt refinement. This underscores the necessity for model-specific prompt engineering to achieve clinical accuracy. This study has several limitations. We did not test the open-source LLMs and did not apply pre-processing to the report, potentially affecting accuracy. Advanced techniques like RAG and fine-tuning were also not utilized. The small-scale dataset limits the study, and larger-scale validation is required for real-world applicability. GPT-4 demonstrated acceptable accuracy in generating NCCN-based structural reports on PDACs from mixed language narrative reports. However, oversight by human radiologists is essential for determining acceptability based on CT findings.